All right, so 5.1. And just want to remind you again of the forces we're looking at. That we have a normal force. This is the force when you have surface contact. We have gravity. Again, this is sometimes called weight. A lot of times, actually, it's called weight. We also have tension, force that's transmitted in a rope. And we won't have any friction for this particular homework, so I'm not going to write that one down. But we also have a force applied. So this is like when a human being or somebody pushes or pulls on something. These are the forces that we're going to be looking at. So let's say we just have a book on a table. And we're going to be then looking, are these four forces here? Again, we're focusing on these four. We're just going to ask ourselves if they're here. Everything with mass will have weight, so gravity coming straight down. There is surface contact. The normal force is always perpendicular with the surface because it's coming out of the surface. That's the normal force. And if no one's pushing or pulling on the block, so there's no rope connected to it, so there's no tension, no one's pushing or pulling on it, so there's no force applied. We looked at our four forces, and there they are. And then what we're going to do is we're going to sum these forces in an x and y direction. Because Newton says when you sum the forces, that equals mass times acceleration. That's Newton's second law. So that's what we're going to do. We're going to sum the forces so we can set this equal to ma. And if we look, and standard coordinate system, unless otherwise stated, so looking in the x direction, there's no forces in the x direction, so that equals 0. And Newton says we can set that equal to ma. And since the mass isn't 0, then certainly the acceleration must be 0. So no acceleration in the x direction. If we look at y, we got our normal force going up. We have the weight going down. And Newton says when you sum the forces, that equals ma. And this is the acceleration in the x direction, the acceleration in the y direction. And here's where you usually have to make the assumption, because a lot of problems won't state this, but when I push my pen along the desktop, my pen's not going up or down. It's not falling through the table. And so this acceleration here is 0 because the block is just moving along the table. It's not going up or down. If it's not going up or down, there's no acceleration in the y direction. And so this is a common assumption that has to be made. The problem won't always state that. Sometimes it'll say it'll be, moving horizontally or something like that to indicate that it's not moving up or down. But either way, from that last equation, we would get that the normal force just equals weight. So the normal force from the table has to balance out the weight in order to support the book there. And this is what we're going to be doing, summing these forces. So just looking at the book here, you can see they have the summation notation for math. And again, physics uses the sum symbol in a pretty lazy way. It just means use the sum. We literally just take it for the word. There's never any numbers in the top or bottom there. So just read that as a word, sum the forces. And for this first one in 5.1, they're telling us these are all systems in equilibrium. So the sum of forces is actually 0 for the whole 5.1 questions. And there's examples in here. Here's where they're showing you to sum forces in the x direction, and then some forces in the y direction here. And again, that's what I'm doing here. Exactly the same type of thing. And we'll go through some homework problems for sure to check it out. And they do have some problems here if you want to check out what the book has to say. And they work out some problems here. There's some forces in the y direction, solving for some tension there. And we have some similar problems that we'll check out, though. But there are some problems in the book here if you want to check them out. And what's different, so just really quick, here's one that's on a ramp. And we have one on a ramp that we'll do too. But when something's on a ramp, it's best mathematically to choose the positive x direction in the direction of motion. So something like this. And again, I'll do a homework problem like this, but when you have a ramp at an angle, that's when using an angled coordinate system tends to make the math easier. That's why we would choose an angled coordinate system. So notice they're doing that for this figure 5.3, the car being towed up the ramp here. They show in their picture the positive x direction is going up the ramp at an angle. And so that is a common thing to do, to rotate your coordinate system so it goes along with the ramp. And this does make the math easier. That's why we would choose to do something like that. So that's not to be weird or anything. It's not some physics thing. Making an angled coordinate system like this literally makes the math easier, is why I'd absolutely encourage you to do that. And for 5.2, again, so a lot of good practice problems here. If you want to check out the book's explanation on how to practice these problems, I will, like I said, go through some problems too, and we'll check it out. Here's another angled coordinate system. You can see the x and y are at an angle here. And again, this is to make the math easier. So some good problems there to check out in 5.1. 5.2 is the same deal. So notice in 5.2, so in 5.1, when you sum the forces, there's going to be no acceleration. That's what they're saying in 5.1. Everything's in static equilibrium. In 5.2, now they're saying when we sum the forces, there will be motion, and so A will be non-zero. And that's what they're saying right here with 4.7. They're saying when we sum the forces, it will equal mass times acceleration. Again, that's Newton's second law. So 5.1, 5.2, it's not that there's really any new physics here. It's just applying now what we have learned. And it's going to be summing these vectors together. Here's another picture of summing some vectors together. And then once we sum our vectors, we'll sum in an x and y direction. We'll set both these equal to mass times acceleration. And then we can figure out things we need to know. Now, once we have acceleration, we could use the kinematic equations. But the truth is that for probably all these problems, once you have the acceleration, that tends to be the answer. So here's another example, some people sliding down a ramp. Notice again that their coordinate system. So people they're sliding down the ramp. They're sliding down the ramp, the people, and they chose a coordinate system such that positive x is in the direction of motion. And again, it's a very common thing to do. It helps the math be a little bit easier. So absolutely something that I'll be doing too when we solve some problems. But a lot of good problems here with free body diagrams to check out. And they do sum the forces if you want to check that out. So a lot of the book's perspective on solving these problems if you want to check that out. But I will also solve these problems from my perspective. So stay tuned for that one.